Radio astronomy is developing very fast, and Jodrell Bank is at the heart of it. When we were last here at Jodrell Bank, we talked about the great 250-foot Lovell radio telescope. This evening, we want to go rather further and talk about new plans and new techniques for radio astronomy for the new century. Light is a wave motion, and the color depends on the wavelength. In visible light, red has the longest wavelength. If the wavelength is longer still, the waves don't affect our eyes. They become radio waves collected by radio telescopes, and they can slice through cosmic dust. Look at this picture, the Crab Nebula, a patch of dust and gas 6,000 light years away. Right in the middle is a pulsar, emitting radio waves. The remnant of a star seen to blow up as a supernova. In Britain, our most famous radio telescope is the 250-foot dish at Jodrell Bank in Cheshire, masterminded by Sir Bernard Lovell in the 1950s and now named after him. It's been responsible for tremendous advances. It's now being upgraded and renovated, and will now be far more sensitive than ever before. The Lovell 250-foot telescope is the most famous in the world. The second big telescope at Jodrell Bank is the Mark II, the rather differently shaped 210-foot. And these are both part of the MERLIN network. These radio telescopes are very powerful on their own, but much more powerful when they work together.
Well, it is a magical instrument. MERLIN is an acronym for Multi-Element Radio-Linked Interferometer Network, and it's been doing fantastic work for the last 20 years. It was actually upgraded in about 1991, and we're planning another upgrade in the next few years.
Microwave radio links are used to bring back the signals from the 7 telescopes making up MERLIN, but they only carry a very small part of the information collected by the telescopes, and so limit the sensitivity. Fiber optics are becoming very important indeed in all branches of astronomy, and here is a fiber. And fiber optics is essential to the updating of MERLIN.
The advantage of fibre optics is that it has a very, very low attenuation in comparison with electrical cables. So we can go further, and we can also have very high-speed bandwidths that we can fit down them.
And what's the real importance in optical and radio astronomy?
The sensitivity of the radio antennas is proportional to the square root of the bandwidth. And because we can get so much bandwidth down the optical fibres, it allows us to take all the information that we get from the receivers in the antenna straight back to the central correlator.
Once in place, these fibre optic cables will help make MERLIN 30 times more sensitive than it is now. So MERLIN, too, is on the threshold of a new era.
Because the upgraded instrument will be so fantastically more capable than the current instrument. For instance, we'll be able to detect things in one day that would have taken the existing instrument 3 years. We have no idea what we're going to see. What we do know is that fundamentally radio telescopes make discoveries. You just have to look at the history, quasars, pulsars, masers, the cosmic microwave background, the fact that 3 Nobel Prizes have been awarded for work in radio astronomy. I think what the upgraded MERLIN will do will be absolutely fantastic in terms of astronomy. Because of the vast sensitivity increase, we'll be able to image a volume of the universe that's more than 100 times greater than that we currently see, with the vast increase in the number of objects that will be visible. We'll run the whole gamut of astronomy, from observing star formation regions in our own galaxy with incredible sensitivity and resolution, looking at evolved stars, microquasars, quasars, gravitational lenses, and star formation very close to the early times of the universe. It would be an instrument with tremendous potential.
You've started the upgrade now to e-MERLIN. When do you hope to finish it?
We hope to complete in about 2007. We have a fairly intensive program of work happening here at Jodrell over the next few years, and we don't have unlimited manpower resources. So we have various things happening between now and 2007 with new capabilities coming online, but the full benefits we hope in early 2007.
Merlin is also part of a worldwide collaboration of radio telescopes called the VLBI, or Very Long Baseline Interferometry. So this is a very interesting map. What does it show?
Well, what it shows is all of the radio telescopes in the world that participate in something called very long baseline interferometry, which is a technique whereby we can get the ultimate resolving power in astronomy. With VLBI, as it's called, we can actually make images with 500 times the resolution that the HST can manage.
And there are various steps on this, aren't there?
Yes, the lights that you see up there at the moment are the what is called the European VLBI network, which is a network of telescopes comprising all the large telescopes in Europe. We have the Lovell telescope, the 100 meter at Effelsberg in Germany, the Italian dishes, the large Westerbork array in the Netherlands, plus also 2 Chinese telescopes.
Yes.
We do a lot of work with the Chinese in all of this. But if we move to what we call the global network, there you can see all the telescopes that participate. So we have the US Very Long Baseline Array, there's a network in Australia and Japan, and then the Europeans.
It's amazing, and I look back. I remember the early 1930s, Karl Jansky began radio astronomy. I met him once, the only radio astronomer in the world. Look at it now.
Yes, I don't think he would ever have believed that we could be this far in 60 years, really.
What about the future of radio astronomy, and where do we go from here?
Adding new telescopes to Merlin is probably not the way to go. The way to go, I think, is to design a brand new telescope. There are 3 ways to increase the sensitivity of a radio telescope. We can make the receivers more sensitive, but really our engineers, very talented engineers, are very close to the theoretical limit of what we can do with receivers. Secondly, we can receive more data, but we're already doing that with the e-MERLIN plans using fiber optics. We're essentially maximizing the amount of data that we can receive. The third way to do it is to build a much larger telescope. Now, we could add more telescopes to Merlin, but we would have to add several hundred to really make an impact. And so astronomers around the world are planning something called the Square Kilometer Array, which is essentially 100 times more collecting area than we currently have in any one instrument. And that's the ultimate goal.
Peter Wilkinson is part of an international team pioneering a new future for radio astronomy. They're going back to the drawing board and coming up with a new radio telescope. The design isn't finalized yet. It has been named the Square Kilometer Array.
Well, the Square Kilometer telescope is not just a number plucked out of the air. People say, why a square kilometer? It sounds just too good to be true. In fact, it's a calculation based on the fact that we want to see hydrogen, the most abundant element in the universe, the simplest element, and it radiates, rather helpfully for radio astronomers, a particular line, the 21 centimeter line. And we'd be able to use that to study nearby galaxies. In fact, if you see here, yes, here we see 2 galaxies, so-called M81 and M82, very close to us actually in the universe. They are galactic neighbors. When you look at it with optical light from a conventional telescope, the galaxies are close to each other but don't appear to be interacting. But when you look at it in the light of the 21 centimeter radiation, the hydrogen, this is a false color image, as if you had radio eyes. You can see the galaxy here, M81, here's M82, but these huge tidal streams of material which have been pulled out as the galaxies, in fact, have passed by each other over the course of cosmic history and gravitationally interacted, and gravity has pulled apart the galaxies and basically tugged them apart from each other. And the material is left out in between the galaxies. You can't see it at all here in the visible light. And we can use these studies of the hydrogen to find out how all these galaxies came to be as they are. Here on the right we see the galaxies, M81 in the middle, M82, and this little companion over here, with all the swirling tidal flows between them. And rather wonderfully, people have been able to simulate this in the computer. Here we see three galaxies colliding with each other, the purple being M81, the yellow being M82, and the green being the companion. Here's M82 coming in, here's companion, and here's M81. A pretty close simulation of what must have occurred for the past several billion years to form this structure here.
Can you tell us a bit about the Square Kilometer telescope project?
Well, what we'd like to do is to study systems like this, but not just on our galactic doorstep, but right out in the distant reaches of the universe, just after galaxies were forming, perhaps a billion years after the Big Bang. And unfortunately, the radio waves from hydrogen are rather weak.
Yes.
So we just have to build a bigger telescope. And if you work out the numbers, you can't use a telescope like the level telescope out of the window here, 76 meters across. You need something a square kilometer across in size, just to collect the weak radio signals to be able to make pictures like these.
It's a worldwide collaboration with a number of different designs being considered. Already are some front runners. One is based on a radio telescope now being built at the SETI Institute to search for intelligent life elsewhere in the galaxy. It's rather like Merlin. It uses several small telescopes linked together. It means many objects can be observed simultaneously. Other designs are being considered. Large spherical lenses or giant video telescopes built in depressions of the ground, such as that at Arecibo.
I must get over the idea that the square kilometer array is not just going to be a giant, even bigger version of Arecibo, a great hole in the ground, a kilometer on the side. No, that's not the way we're going to do it. These days we want to build what's called an interferometer, where we split the dish up into little bits. So what we'll do is build it out of perhaps little dishes, perhaps another way, but perhaps little dishes, perhaps only 10 meters across. And in fact, one of the concepts, the so-called Allen telescope array, uses satellite TV technology, commercial technology, to build lots and lots and lots of very cheap dishes to synthesize, to build up a much bigger telescope, in this case one 100 meters across.
When will the Square Kilometer array be ready, and where will it be?
Well, all big projects, and this is a huge global project, far beyond the capabilities of any individual nation to put together. So this is a global project, and it takes about 15 years. So we are imagining sometime in the middle of the next decade this will be operational. Lots and lots of R&D, research and development, needs to be done in the meantime. One of the problems, because we want to study the hydrogen from the universe, one of the problems is that hydrogen, 21 centimeter radiation, but the expansion of the universe from a distant galaxy stretches that radiation to perhaps a meter and beyond. Well, unfortunately, meter radiation is right in the middle of the bands used for communications, mobile phones and the like. And so we have to put the square kilometer somewhere where people aren't. So in a low population density part of the world, perhaps Australia, perhaps South Africa, perhaps Argentina, something like that, where there are few people and there are no, therefore, radio radiations to affect our radio astronomy.
When it's working, and I hope it will be, what do you hope it will show you?
Well, the thing I'm most interested in is the study of hydrogen from the distant universe, seeing how galaxies formed just after the Big Bang. We're very good at studying the Big Bang now. There are lots of satellites and ground-based observations telling us about the so-called cosmic background radiation and the little ripples in it, which must have been the precursors of galaxies themselves. But what we have very little knowledge about at all is how, from the Big Bang, from that very smooth distribution of matter, the rather clumpy distribution of matter, the galaxies, the stars, formed. There's a long period in the universe's history about which we know very little. The square kilometer array could be perhaps the first telescope to tell us about that.
I'm afraid I won't see that, but I hope you will.
Well, I hope so. I'll be retired, but I hope to be invited to the opening ceremony.
Once the square kilometer array is completed, we'll be able to look even further back in time, to no more than 1,000 million years after the universe came into being, something like 14,000 million years ago. Jodrell Bank astronomers are working with astronomers from Cambridge and Tenerife on Mount Teede in the Canary Islands. The main enemy of the radio astronomer is water vapor. It absorbs radio waves, and the only real answer is to go out into space. In 2007, the Planck satellite will be launched by a French Ariane rocket to study the cosmic and microwave background. It will be far more sensitive than anything previously attempted. Some of the receivers are being built here at Jodrell Bank, and here's one of those. Danielle, welcome to the sky tonight.
Thank you.
What are the main points about this receiver?
Well, this sort of brass block here houses the amplifiers that are being built at Jodrell Bank. We are building the 30 gigahertz and the 44 gigahertz for the Planck satellite. There are also 70 and 100 gigahertz. So this houses our amplifiers, which are built by Eddie Blackhurst, our technician.
When do you hope to finish?
There are several stages to it. We hope to build what's known as a qualification model by the end of the year.
I mean, it means it's fit to launch into space.
That's right, yeah, just so it withstands the launch. And then we build the actual flight models after that. It's then sent to Italy. So all of the modules are housed together, and then the whole testing of the Planck satellite will be done before the launch in 2007.
And let's hope for a really successful launch. Daniel, thank you very much.
Thank you.
It's going to enable us to study the so-called cosmic microwave background, what the universe was like just 300,000 years after its origin, with far greater precision than we can at present. We have telescopes we operate now with the Cambridge University group on Mount Tidy in Tenerife, and the others around the world. They've told us a lot about the universe. We now know pretty much how much matter and energy it contains. We also know that only about a third of that is in the form of matter. And only a sixth of that is in the form of matter that make up you and I, and the stars and everything we see in the universe, normal matter. That other 25% is sort of dark matter. We know it's there, we can't see it, we don't really know what it is. But in total, that still only makes up about 30% of all the mass and energy in the universe. It appears that the other 70% is in the form of some dark energy, sort of an energy of the vacuum of space that appears to be making the universe expand at an ever-increasing rate. Really quite amazing. Now we know pretty much these numbers, 4% of normal matter, 25% dark matter, and perhaps 70% of this dark energy. But Planck is going to enable us to refine those far, far better, and maybe help us to understand these sort of fundamental mysteries of the universe.
In a way, it's strange to recall that radio astronomy is such a very young science. It began only in the 1930s. It's come a long way. And I wonder, where is it going to go in the years to come? I think the answer is a very long way. There is still time to enter our astrophotography competition. Details on our website, www.bbc.co.uk/space, and CFAX page 620. And best of luck. And so until next month, good night.